We're extremely happy to have Yingni presented her paper on robust monopoly regulation. You have about 1 hour to present it, and we will interrupt you with questions as we go. Okay. Please take it away.
Okay, thank you, Anton. Thank you everyone for coming. So this is joint work with Iran from Stony Brook. Okay, so we all know that regulating monopolies is a notoriously challenging problem. A monopoly firm has the market power to set its price above that in a competitive or oligopoly market. Right. For instance, this QJE paper by Cooper and his co-authors shows that prices at the monopoly hospitals are 12% higher than prices in markets with 4 or 5 rivals. This chart shows the price premium for different procedures. Okay. Now, in order to protect consumers, a regulator may want to constrain a monopoly firm's prices. However, a price-constrained firm may fail to obtain enough revenue to cover its fixed cost, so it may end up either not producing or underproducing. Right? Now, the regulator must balance the need to protect consumers and the need to not distort production. Now, this challenge could be solved very, very easily if the regulator had complete information about the industry, right? So if a regulator knows the demand curve, the demand curve, right? So this is Q and this is P, and the marginal cost, he would ask the firm to produce the efficient quantity and to price at this efficient quantity. He would then subsidize the firm for all of its other costs, right? So in particular, monopoly utility firms typically have huge fixed costs. Right? Now, in this paper, we want to understand what the regulator should do when he knows much, much less about the industry than the firm does. In particular, if the regulator demands robustness and wants a policy that works fairly well in all the circumstances, what should this policy look like? Okay. Now, in this paper, we address this classic monopoly regulation problem using a non-Bayesian approach. As in the Bayesian approach, we assume that the regulator's payoff is a weighted sum of consumer surplus and the firm's profit. Okay, the parameter alpha is the weight that the regulator puts on the firm's profit, and we consider alpha between 0 and 1. Okay, now our regulator has access to all kinds of instruments. He can regulate the firm's price and or quantity. He can give a subsidy to the firm, or he can charge a tax from the firm. So both sides, both the regulator and the firm have deep pockets. Okay. Now, given a regulation policy, the firm will observe its demand and cost functions, and the firm would choose a price and a quantity to maximize its profit. Now, we can calculate the regret to the regulator, which is the difference between the payoff that the regulator could achieve if he had complete information and the realized payoff of the regulator. Now, you can think about this regret as the money left on the table due to the lack of information from the regulator. Now, in this paper, we want to find the policy that minimizes the worst case regret that the regulator could have. And this worst case is taken across all possible demand and cost scenarios, and the minimization is across all possible policies. Okay, any questions so far?
Yes, a quick question. So when you say that the regulator can give a subsidy or tax, so there, you put some restrictions on the set of feasible mechanisms that regulator can use, or not?
We don't put any, So basically, what I meant here is that there is no limited liability on either side. There is no liquid constraint. Yeah.
Great, thank you.
Liquidity constraint. Yeah, thank you.
But so on a related note, right? So one of the rationales for Ramsey pricing would be that the government cannot, for reasons that are outside the model, cannot subsidize the firm, right? So there's a whole bunch of potential issues that derive from these transfers that occur if the government starts using taxpayers' money to pour that into the private industry. So then the question arises, in what sense is this going to be robust? I mean, it's going to be robust with respect to distribution, I suppose, but is this really what we think should be done in reality?
I see. So I think the what do we do here? So you can think about the problem in which there are actually, that's a very good direction, right? So one direction we can take is to assume that for each dollar that the government subsidizes the firm, it actually costs the taxpayer 1 plus lambda, right? So this lambda can be thought of as the kind of the cost of public funds, right? If this lambda is infinity, then the government wouldn't wouldn't subsidize the firm, right? So it's too costly on the consumer or on the taxpayers. In this paper, we kind of take the Barry-Myers approach by assuming that there is no cost of public funding. And we do that because we also want to focus purely on the information asymmetry. We don't want to touch public financing side, but going forward, that's also something we can explore using the framework. Yeah.
Okay, thanks.
Thank you.
So one more question about the objective to minimize the maximum regret. So I mean, potentially you could also like maximize the minimum profits that you get, or have some mixed objective between maximizing regret and guaranteeing some profit. So can you comment on why you chose this objective?
Yes, so it's actually, you will see this also at the conclusion side, and you will see this very quickly that the regret has a very natural interpretation in this model. It is a weighted sum of firm's profit and the distortion in production. So the distortion captures the inefficiency, and the firm's profit captures the redistribution objective of the regulator. So that's one reason. And the other reason is that, so these two approaches, this first approach minimize the worst case regret, is more targeting market scenarios in which there are a lot of surplus in the market, right? So there is a lot of surplus in the market. I want to make sure that I achieve close to the best potential. And the maximize minimum payoff is targeting those market scenarios in which there is very little surplus in the market. So in the sense that when there is very little surplus, for example, this goes back to Simon's question. If you are thinking about maximizing minimum payoff, you wouldn't want to subsidize, because subsidize might cost you money without cure the distortion. So these two approaches, one is focusing on high surplus market scenario, one is focusing on low surplus market scenario. Yeah, in particular, in our framework, you will see if you want to maximize minimum payoff, the optimal policy is to do nothing. Yeah. So from this aspect, yeah, you can think about our approach as to protect the surplus when there is a lot of surplus to protect. Yeah. Thank you, Anton. Yeah, I'll move on. Okay, now what do we, before going to the model, I want to have a very quick overview of what we got. So I will talk about the two extreme payoffs by the regulator. So remember that the regulator's payoff is consumer surplus plus alpha times firm's profit. So when alpha is equal to 0, the regulator's payoff is consumer surplus. In this case, he's solely concerned about consumer well-being. He wants to redistribute, right? And we show that the optimal policy is simply to impose a price cap. Now, a price cap will, when the government imposes a price cap, consumers might gain from a lower price. However, they might lose from the firm's underproduction. So the optimal price cap will balance the gain from lower price and the loss from underproduction. at the other extreme, when alpha is equal to 1, this is a very different objective, right? So this regulator wants to maximize the total surplus of consumers and the firm. So he wants to do the efficient thing. And we know that a monopoly firm tends to undersupply, right? So a monopoly firm tends to just supply the first few consumers who are willing to pay a lot. So in this case, the regulator wants to encourage more production by offering a piece rate subsidy, which effectively increases the revenue per unit of the firm. On the other hand, the regulator would cap the total subsidy he is willing to give, so he doesn't incentivize too much overproduction through his subsidy. Now, the optimal policy, the optimal piece rate and the cap subsidy balances the loss from underproduction and the loss from overproduction. Okay. Now, for every parameter alpha in between, the optimal policy is a combination of this price cap and the piece rate subsidy rule. Okay. So I see a raising hand.
Hi,
yeah.
Yingni.
Hi.
My name is Novin from Deakin University. I have just a clarification in here. So when you do these things, this is a monopoly who's just producing a single goods and he does not discriminate the price.
Very good question.
He's also not producing a damaged goods.
So he's producing a single unit, single good, and we are thinking about the uniform pricing. Yeah.
Okay. So okay. Thank you.
Thank you. Yeah. Okay. Now we will see that the optimal policy basically would balance 3 objectives from the regulator. So he wants to give more surplus to the consumers. He wants to mitigate the underproduction that is intrinsic in a monopoly problem. He also wants to make sure that his subsidy does not incentivize too much overproduction. Okay. Now, are there any questions at this stage?
Stupid question. So why not allow alpha to be greater than 1?
So this also is related to the discussion about the public funds, right? So if alpha is greater than 1, and because here we assume that $1 from consumer, so we don't assume any cost of public funds, the regulator would tax consumers and give all the money to the firm, right? So that's what happens. Okay. So I will have a very brief literature review by focusing on the most related papers. So this, of course, we are related to this strand of monopoly regulations that which started from Barry and Meyerson. And in Barry, Meyerson, Louis Sappington and Armstrong, they basically assign a prior belief over the cost and the demand functions, and then they try to maximize the expected payoff of the regulator, which is the same as minimizing the expected regret of the regulator, right? So Barry and Meyerson look at cost uncertainty. Louis Sappington, they look at demand uncertainty, and the second paper looks at both demand and cost uncertainty. The same for Armstrong. Okay, so in our paper, the type space of the firm is much larger, and also we take a non-Bayesian approach by looking at the policy that minimize the worst case regret, which brings us to this second strand, which is a mechanism design with worst case regret approach. And we also contribute to the growing robust mechanism design literature. Lastly, I want to talk a little bit about the delegation. So some of you might know that my job market paper was on delegation. So when I was on the job market, many people ask me why people use contracts that do not use money, right? So why don't we just make transfers to each other? We see delegation contracts very frequently in reality, but in this paper, we kind of provide a micro foundation for delegation contract in the sense that the firm and the regulator can make transfers to each other, but a price cap policy sometimes is optimal. Okay. Now, if there is no question, I'll move on to the model section. Okay. Can you see the slides? Still okay, perfect. Okay, so so the model section is the standard monopoly regulation problem. There is a monopoly firm and there is a mass one of consumers, and the firm's demand function is given by capital V. This is from unit interval to 0 V upper bar. So we assume that the highest valuation the consumer can have is V upper bar. And we say that a quantity price pair is feasible if it lives below the demand function. So the firm can choose any quantity price pair that is feasible given his demand function. And then we assume that the cost function is given by C and is a function from the unit interval to the positive real line. Okay, so the firm can choose not to produce, which has a zero cost, and the cost function is weakly increasing. Okay, now we are going to, in the baseline model, we just assume that all types of demand and cost functions, given these conditions, are feasible, are possible. Okay, now given a cost demand function, we can characterize the maximum total surplus in the market. So I should put a parenthesis here. Basically, this is given by the total value to consumers if the firm produces Q units minus the cost of producing Q units, and we maximize over Q. So that is the efficient quantity that the firm should produce, right? So if the firm instead produces Q units, the distortion is given by the maximum total surplus and the actual surplus. Okay. Now, before moving on, I want to talk about two kind of market scenarios which will show up later on. And the first one is given by this picture. So in this market scenario, the first two-thirds, Simon, yeah.
Yeah, sorry, I could let you finish first, but the formulation you have assumes that the firm, so I suppose there's information such that the regulator doesn't know the realizations of V and C, but
yeah.
the monopoly does, right? But then you're also restricting attention to the monopoly setting a market clearing price, right?
Oh, actually, that's actually, I was not clear enough. So actually I allow monopoly not to clear the market. So anything that is below the, so if this is the V function, demand, inverse demand function, all these points are feasible points for the firm.
Okay, let me rephrase it. You restrict the monopoly to set a uniform price.
Yes.
And then otherwise your formulas for social surplus are not correct, right? If there's some random rationing going on or something, then that would be different.
Oh, that's a very good question. That's so I haven't. So you are 2 slides ahead because I haven't defined what is consumer surplus and what is firm's profit. Here I do assume that efficient rationing, just to simplify notation. But later on we show that if the cost function satisfies condition that the average cost is decreasing, then the firm would always choose to clear the market. So the efficient rationing assumption is not needed. However, without that assumption on the cost function, efficient rationing assumption is needed. Yeah.
Okay.
Okay. So I'll talk about that when we talk about the demand the consumer surplus. Yeah.
All right. Now I'm too many slides ahead, but just out of curiosity, you're not making assumptions on the curvature of the demand function?
No, we're not. As long as it's weakly decreasing, so any upper semi-continuous decreasing function are considered. Yeah.
Okay. Thanks.
So this is kind of the demand function that is likely to invite underproduction. So in this demand function, the first 2/3 of the consumers have the highest valuation V upper bar, and then starting from 2/3, we have the unit elastic demand, right? And then the cost of production is equal to 0. So in this market, the firm is indifferent among all these points of this unit demand, unit elastic demand section. And then if we tilt this demand function a little bit down here, the firm would just choose 2/3, right? So in this case, the market distortion is given by this light blue area. And we say that the firm underproduces, right? So the firm is producing less than the efficient quantity. Okay, let's look at the second example. So this is an example in which the first 2/2 of the consumers have valuation half V bar, and the rest have valuation 0, and the cost of production is 1/3 V bar. So in this market, if the firm actually chooses to produce 1/2, the distortion the firm should not produce, right? The fixed cost is too high relative to the total consumer value, which is 1/4 V upper bar. So if the firm actually chooses to produce, the distortion is the maximum total surplus minus the realized surplus is still a positive number. So by definition, distortion is always a positive number. And in this case, we say that the firm overproduces. Okay, so this is a type of firm that the regulator wants to be aware that he doesn't want to incentivize this type of firm to produce just to get a subsidy. Okay, so that's kind of, I'll talk about that later. Okay, now going back to the model, we assume that the regulator can observe both the quantity and the price chosen by the firm. So a policy is given by a rho function such that if the firm produces Q units at price P, then it receives a total revenue of rho QP. Okay, this rho QP includes the market revenue and any tax or subsidy from the firm, from the regulator. Okay, now if rho QP is greater than QP, it means that the firm actually gets a subsidy of rho QP minus QP. If rho QP is equal to QP, then it actually, for every Q and every P, it shows that the firm is unregulated, right, effectively. Now, we also assume that the firm can stay out of the business with a profit of 0. That's the participation constraint. Now, let's look at a few regulation policies that sometimes people use. So the first one is called a lump sum subsidy. So this is a subsidy which tries to incentivize the firm to produce at least a certain amount, right? So in this case, the subsidy rule says that if you produce less than Q tilde, you just get your market revenue. If you produce more than Q tilde, you get a subsidy of W. Right? Question? Okay, no. So now the second one is a familiar one, a price cap K, right? This basically says that if you price above K, this is not allowed, right? The revenue is minus infinity. And if you price above K, below K, you get the market revenue. Right, so just tells you that you can price below K. And then the third one is a cap K on the revenue per unit. And this basically says that your revenue is equal to the minimum of QP or QK. And this, we actually, in the paper, we show that these two policies are effectively the same, right? They induce the same outcome. And the fourth one is a proportional tax. Basically, this policy says that I'm going to take a tau fraction of your total revenue away. Right, so if you think about planned economy where the state-owned monopolies are the source of tax revenue, they sometimes use this type of policy. And the last one is a lump sum tax. So this basically tells the regulator, the firm that I would take W away from you. Right, so this relates to the recent fine Alibaba faces in China. They have to pay 2.8 billion antitrust fine, right, for monopoly behavior. Okay, now we want to show in the paper that actually the price cap shows up in the optimal policy, but the other instruments do not. Okay. Now let's go back to the model. The timing of the game is what we said before. The regulator first chooses and commits to a policy role, and the firm privately observes there is a typo here, its demand and cost function. It chooses a quantity price pair to obtain the market revenue, and then the regulator transfers rho QP minus QP to the firm. So if this is negative, this means that it's a tax. Okay, questions so far? Now I'm going to talk a little bit about what Simon has asked. So fix a policy role and the fixed demand and cost, the scenario VC. If the firm sells Q units at the price P, the firm's profit is rho QP is revenue minus the cost. Now consumer surplus is the total value up to Q minus rho QP, right? So here, actually, this consumer surplus is related to both assumptions that Simon has raised. The first assumption is that we assume efficient rationing. Right? So if the firm does not clear the market, we assume that the highest valued consumers are served. The second one is that a dollar to the firm is actually $1 from the consumer, right? $1 from the consumer. So any tax to the firm any tax from the firm goes to the consumer, and any subsidy to the firm comes from the consumer. So we don't assume any cost of public funding. Now, QP is the best response to a VC demand and cost on the policy role if it maximizes the firm's profit among all the feasible Q and all the feasible QP pairs. The regulator's payoff is a weighted sum of consumer surplus and the firm's profit. Any questions? Okay, if not, so up to this point, everything I said is standard. Our only departure is in the regulator's payoff. So we assume that, sorry, I'm jumping ahead. So we assume that instead of maximizing the regulator's expect payoff, instead we want to minimize his worst case regret. So for that discussion, I want to talk about the complete information benchmark. So what happens when the regulator knows the demand and the cost functions, and he can choose a policy according to that knowledge. This claim shows that if the regulator knows V and C, then he can choose a policy to make sure that he gets the maximum total surplus in the market. So his payoff is equal to the maximum total surplus if he knows V and C, right? The optimal policy is very simple. Basically, what a regulator would do is to first calculate the efficient quantity, Q star, and he tells the firm that if you produce Q star and you price at the marginal value at the Q star, I would make sure that your revenue is equal to your cost. If you do everything else, I would give you a zero revenue, right? So in fact, if you can put an epsilon here, so that firm is strictly willing to do the efficient thing. And in this case, the maximum total surplus is generated, and all of this surplus goes to the consumers. This is why, even though the regulator's payoff depends on alpha, the maximum total surplus is independent of alpha, right? Because all the surplus goes to the consumer. Question?
Hi, Yingni. Just for clarification again, we claim if the regulator knows V and C, then what is the role of alpha then? Because I can always take the surplus, right? Which is your integral minus your cost. And then alpha will be 1 in this case. So what is the role of alpha when regulator knows exactly what the V and C is?
Oh, so this is exactly what I was saying, right? So if I know V and C, then my policy would, as long as alpha is smaller than 1, I would make sure that all the surplus goes to the consumers, right?
Okay. But I thought if V and C is known, then alpha should be 1, right? That's what the regulator do, right?
Oh, no, alpha is capturing the regulator's objective. So if the regulator alpha is smaller than 1, it just shows that this regulator has some redistribution objective, right? So I want to make sure that profit goes to, profit goes to the consumers instead of the firm.
Okay, so it's just a transferring these things, right?
Yes, yes.
Okay, yeah, thank you.
Yeah, you're welcome. So now this is the complete information payoff. Now let's look at, this allows us to actually simplify the regret expression of the regulator dramatically. So remember that the regret is the difference between complete information payoff and the actual payoff. Now the complete information payoff is the maximum total surplus. The actual payoff is consumer surplus plus alpha times firm's profit. If we do a little bit of algebra, eventually this is a sum of the distortion plus 1 minus alpha times firm's profit. So this shows that whenever there is $1 of distortion, my regret goes up by $1. Whenever there is $1 of firm's profit, my regret goes up by 1 minus alpha, right? And that's the decomposition we discussed a little bit at the introduction. And this regret, in particular, when alpha is equal to 1, going back to the previous question, my regret is just equal to the distortion. I want to make sure that the firm produces as efficiently as possible. When alpha is equal to 0, firm's profit punishes me as much as the distortion punishes the regulator, right? So that's kind of the decomposition we discussed. Now let's look at the regulator's problem. The regulator does not, in an environment, if the regulator has a prior belief over the demand cost function, a natural thing to do is to find a policy to minimize the expected regret, which is the same as maximizing the expected payoff. Now, we are interested in an environment in which it's not easy to formulate a prior belief. It's not clear how the regulator should formulate a prior belief. Instead, he would try to find a policy that minimizes the worst case regret. And this maximization is over all the possible demand and cost scenarios, and the minimization is over all the possible policy role we discussed. Questions? Okay, if not, I'll move on to the main result. So for this type of robust design paper, the typical approach is to show that no matter how the regulator chooses his policy, he has to suffer a sufficient amount of regret. That's a lower bound on the worst case regret, right? So I try to convince you that no matter what the regulator does, the worst case regret is at least this much. And then in the second part, we show that our optimal policy exactly achieves this worst case regret. So it is optimal. Okay. Now, let's first move on to the lower bound on worst case regret. I want to begin with a very simple policy just to warm up a little bit. Right? Suppose the regulator just imposes a price cap K. So let's think about what this policy would do in different market scenarios. Okay, so on the left-hand side, this is the first market scenario. I call this the face mask example. So think about this is at the beginning of the pandemic. Everyone wants to buy a face mask, or everyone wants to buy some equipment for the pandemic. And now face mask is very easy to produce. So we just make it very simple. Suppose that the cost of production is 0. Right, so regulator says, okay, the firm cannot price above K, right? So this is my policy. Now, in this policy, under this policy, in this market scenario, the firm would would serve the whole market, and there would be no distortion. And the firm would price at K, so the firm's profit is equal to K dollars, and the regret is coming from the redistribution objective, 1 minus alpha times K, right? So in fact, if the regulator knew that this is the market scenario, he would impose a price cap at 0, right? So he would tell the firm just to price at 0 for its products. Now, the lower the price cap is, the lower the regret is, the better the regulator feels. Now let's look at the other side. It's still the face mask example. However, there is a fixed cost to transform the factory into a safe environment for production, right? So suppose that this fixed cost is K or K plus epsilon. Now the regulation exactly prevents the firm from production. Now, in this case, the firm would tell the regulator that, sorry, the price cap is too low, I choose to opt out, right? So in this case, the distortion is equal to V upper bar minus K, which is the surplus that could have been generated, and the firm's profit is equal to 0. So the regret purely comes from the distortion, V upper bar minus K. Now, the lower K is, the worse the regulator feels, right? So if the regulator knows this is the environment, he would make sure that price cap is above the fixed cost. Now you can see that there is a trade-off between giving more surplus to the consumers and the underproduction through this example. And we can summarize this example. Also, there is a price cap K which balances this trade-off, and this is the price cap that equates the regret from left-hand side and the regret from right-hand side, and we call it K alpha. We also can summarize the discussion into our first claim, right? So the worst case regret under any policy is at least 1 minus alpha times K alpha, right? So no matter how you design the policy, if you give the revenue more than K to the firm, you might have too much loss from redistribution. If you give too little revenue to the firm, you might have a lot of loss from underproduction. Okay, so no matter what you do, you have to suffer this much regret. Okay. Now this picture shows the value of K alpha as a function of alpha is from 0 to 1 and is equal to half V bar when alpha is equal to 0 and is equal to V bar when alpha is equal to 1. So intuitively, when you don't care about the redistribution, you wouldn't impose a price cap, right? So you actually don't want to impose a price cap at all. Now, on the right-hand side, this is the first lower bound we establish through this simple example. I will show you that actually this is not a tight, right? So for alpha above 1/2, the worst case regret is higher. That's what our first theorem here is doing. Okay. Any question about this simple illustrating example? Okay, if not, I'll move to the first theorem. Okay, so this is actually a tight lower bound. And let's forget about the algebra on this slide. The main idea is that for any Q and P, we can define a lower bound function. And this lower bound function is the minimum of two terms. The first term is the regret from underproduction. The second term is the regret from overproduction. So no matter how you design your policy, you either suffer from the first term or you suffer from the second term. So that means your regret is at least the minimum of these two terms. Okay. Now, given that this is true for any Q and any P, so the worst case regret on any policy is at least the maximum of this lower bound function across all the Q and all the P's. Okay. So that's kind of the rough idea of this theorem. Now, I would walk you through this. So this theorem basically would incorporate on top of the claim we have seen the regret from overproduction. And I'll just show you why we would have a higher lower bound than before. Okay, now let's look at this, the proof idea of this theorem. Please give me an arbitrary policy rho, and we can pick any Q and P, right? So this is a Q and P I picked. And then let's look at this demand function, which is likely to induce underproduction. So under this demand function, the first Q consumers have the highest valuation. And starting from Q consumers, starting from P, we have the unit elastic demand. Okay. Now, if you are thinking if the firm is not regulated, this firm would never go beyond Q. Right, so he would choosing QP would give him, choosing QV upper bar would give him a revenue of QV upper bar, but for anything beyond that Q point, his revenue is Q times P. Okay, so this is kind of the a serious underproduction problem the regulator is concerned about. Okay, now let's think about what happens under the policy rho you gave me, and I can find the term X, which is the maximum revenue that the firm would get if it does not go beyond Q. Okay, so if I choose a point here, X is the maximum revenue I would get under your policy. Okay, now Y is the maximum revenue I would get if the firm goes beyond the Q. Okay, now let's think about what possible values X and Y can have, and we can think about 3 different scenarios. The first scenario is that both X and Y are very small, right? Suppose the maximum of X and Y are smaller than Q times K alpha. In this case, this is similar to the simple example we've seen before, right? So if you impose a very low bound on the maximum revenue the firm can get, suppose that the firm has a fixed cost of Q times K alpha, this firm would not produce. Now, the regret is equal to the distortion in the market, which is equal to the total consumer surplus minus the fixed cost, which is the first term in our lower bound function. Right. So this is the first term in our lower bound function. So that's why it's higher than the lower bound function. Okay. Now, what's the second scenario? The second scenario is that the maximum of X and Y is greater than Q times K alpha, but X is greater than Y. So in this case, if X is greater than Y, a firm with this demand function and the zero cost would never go beyond the Q. Now you are going to suffer regret from two fronts. The first front is that you still have a lot of distortion, which is equal to the total surplus in this area, because the firm would not go beyond the Q. And the second source of regret is that the firm will get a lot of profit, right? So it's equal to 1 minus alpha times X, which is at least the Q times K alpha. This is again the first term in our lower bound function, and that's going to be greater than our lower bound function. Okay. Now, what's the third scenario? The third scenario is that you really want to incentivize the firm to go beyond the Q, right? So the only thing you can, the only way to achieve that is that you subsidize the firm a lot if the firm goes beyond Q. So this is the third scenario. The max of X and Y is greater than Q times K alpha, and the Y is greater than X. Right. So this means that in one point in this blue area, the firm can get a lot of subsidy from the regulator, potentially high subsidy from the regulator. Now, in this case, we let Q and the Q prime and P prime be a point in the blue area such that the revenue at that point is equal to Y, which is greater than Q times K alpha. Now, on the other hand, so if this is Q prime and P prime, on the other hand, suppose the firm actually has this type of demand and cost function, right? So the firm has a function such that exactly Q prime consumers have the valuation P prime, and there is a fixed cost of Y from production. Now, this firm has a very minimal consumer value, but this consumer value is high enough to actually achieve this surplus from the regulator. So in this case, the right-hand side would generate a regret, which is equal to the distortion, which is equal to the fixed cost minus the total consumer value in this market, which is the second term, at least our second term in the lower bound function. Right, so this is kind of the intuition. This picture shows the intuition, the trade-off between underproduction and overproduction, right? So either you give up this Y area and you don't incentivize the firm to go beyond Q, or you incentivize the firm to go beyond the Q, then you have to subsidize the firm a lot. Now you subsidize, once you offer subsidy, this type of firm might jump onto the ship to get this subsidy, and that's causing some regret from overproduction. Okay. And so our lower bound theorem just shows that the worst case regret under any policy is at least the maximum over QP of this lower bound function, and we use R alpha to represent this lower bound. Okay, and the right-hand side picture shows the value of R alpha as a function of alpha from 0 to 1. So as you can see, it's actually higher than the previous lower bound function we have achieved. Any questions? Yes, here's something. Okay, if not, I'll move on to the optimal policy, the real thing of the paper. So we are going to show you that our optimal policy would exactly make sure that the firm does not suffer more than the lower bound of this worst case regret. Okay, so again, I'm going to discuss the two extreme cases of the regulator's payoff. The first one is the extreme when alpha is equal to 0. Okay, so in this case, the regulator's payoff is consumer surplus. Okay, so our first theorem says that if the firm imposes a price cap K0, which is equal to half V bar, then his worst case, the regulator's worst case regret, sorry, the regulator imposes a price cap half V bar, then his worst case regret is at the most half V bar. Okay, so this shows that this policy is optimal. Okay. Now, the proof for this result is by revelation principle. Now, suppose that the regulator imposes a price cap at half V bar. Now, consider any demand function you can think about given by this picture. Now, suppose the firm tells the regulator that the regulation is too strict and the firm prefers not to produce. I want to convince you that the total surplus in this market is at most half V bar. So in this case, the regulator would not lose more than half VBAR in terms of regret. Okay, now let's first look at these consumers. So these consumers, they value the product below half VBAR. So each one of them contributes at most half VBAR to the total surplus. Okay, so now they don't add more than half VBAR to total surplus, so the regulator does not lose more than half VBAR per person. Now let's look at the first area, right? So these are the consumers who value the product very highly, and potentially the regulator can lose a lot of total surplus. On the other hand, the firm chooses not to produce under the price cap half VBAR. So there is only one reason for that. The reason is that the average cost of serving these consumers must be higher than half VBAR, right? So if you give me a price cap of half VBAR and I can charge a price at half VBAR, but I choose not to produce. The only reason is that the average cost is more than half VBAR. So this means that for the consumers who value the product very highly, each one of them contributes at most half VBAR to the total surplus as well. So this shows that the total surplus in the market is at most half VBAR. Now, let's look at the second scenario. The second scenario is that the firm tells the regulator, I still want to produce. So I want to produce Q units. And now for all the consumers who are to the right-hand side of Q units, the argument is the same as before, right? So either they don't contribute more than half VBAR per consumer, or the additional average cost of serving these consumers is higher than half VBAR. Okay, so that means we don't lose more than half VBAR per person. For the consumers between 0 and Q, the cost could be very small for the firm. And in this case, the price cap makes sure that the firm does not extract more than half VBAR per person. So this also makes sure that the regulator does not lose more than half VBAR per person. Okay. So that's the kind of the revealed preference argument for this result. Questions? Okay, if not, let me look at the other extreme, right? So the other extreme is this regulator whose alpha is equal to 1. Okay, so this regulator's mentality is very different. His payoff is the joint surplus of consumer and firm's profit, consumer surplus and firm's profit. We show that the worst case regret is at most the lower bound R1, given the following policy. This policy tells the firm that your total revenue is the minimum of 2 terms. The first term is telling you that, okay, if you price below V upper bar, I would subsidize you for the difference between your price and V upper bar. So effectively, I'm creating some consumers who are willing to pay the maximum amount for the firm, the maximum amount of V upper bar for the firm's product. Okay, so this is the piece rate subsidy we were talking about. I want to subsidize you for the difference between your price and the V upper bar. On top of that, I would tell you that the total subsidy I would offer is at most R1. Okay, so this is kind of the policy such that the regulator wants to incentivize the firm to produce a little bit more than the monopoly quantity. On the other hand, the regulator would tell the firm that at some point the subsidy would stop, right? So this is how the regulator balance the regret from underproduction and overproduction. Okay, so the next picture shows the proof idea of this result. And suppose we have this type of demand function and the cost of production is equal to 0. So in this type of market, if we don't regulate at all, the firm would stop at this point. Right, so now the regulator would lose all these areas in terms of regret, right? So I would regret that I didn't incentivize the firm to produce a little bit more. Now the regulator tells the firm that if you go beyond that point, if you choose this price and quantity pair, I would subsidize you for the difference between your price and the highest willingness to pay. So in this case, we effectively create more maximum willingness to pay consumers for the firm. So the firm is willing to do a little bit more, right? So the firm is willing, for example, to stop at this Q and the P pair. And now at this point, the regret for the regulator would shrink to this smaller area. On the other hand, the regulator is giving the firm this gray area of subsidy. So this subsidy might potentially incentivize an inefficient firm to produce. So the optimal policy basically balance the area of this light blue area, which is the regret from underproduction, and the area from this light gray area, which is the regret from overproduction. So that is the main intuition of this optimal policy. Okay. Any questions? Okay. If not, now I would show you the optimal policy for everything in between, right? So for everything between 0 and 1 of the value alpha, the worst case regret is at most R alpha, given the policy below. So this policy is the minimum of 2 terms. The first term is Q times K alpha. The second term is QP plus S. So this S can be anything between S alpha and the R alpha. I don't have time to talk about the particular definition of S alpha, but this blue line gives the value of S alpha and this gray line gives the value of R alpha. So anything between these 2 lines are possible cap on the total subsidy. Now this policy tells the firm 3 things. First of all, you are not allowed to get more than K alpha per unit, right? So this cap on the revenue per unit on the firm would make sure that the firm does not extract too much surplus from the consumers. So this is in order to protect the consumer well-being by constraining the surplus the firm can extract. The second idea under this policy is that if you produce very little and you price below this K alpha, I would subsidize you for the difference between your price and the K alpha. So this is a piece rate subsidy, which effectively makes sure that the firm can get K alpha per unit initially. Okay. And the third idea is that, so this second idea is to make sure that the firm does not underproduce too much, which is an intrinsic problem in the monopoly regulation problem. And the third idea is that the total subsidy the firm can get is at the most S. So I would not subsidize you for more than S unit, for more than S in total. Okay, this is to make sure that the firm, we don't lose too much from overproduction. Okay, so now these 3 objectives are there in order to address 3 concerns. So the cap on the revenue per unit will cap how much consumer surplus the firm can extract. The firm would get a piece rate subsidy up to K alpha. This would effectively increases the firm's revenue per unit to K alpha initially. And lastly, the firm's total subsidy is at most S. So we don't incentivize too much overproduction from the regulator, from the firm. So if we go back to Simon's question about the cost of public funds, I think that would just imply that the cap would be lower, right? So if there is a cost from public funds. So in this case, we would like to constrain how much we will transfer to the firm in total. Okay. So this policy actually, the policy we have provides a micro foundation to the price cap regulation. So price cap regulation initially was used by British telecom, gas, airports, water, electricity, and the railway industries. In the US telecommunication industry, between 1985 to 1999, initially 50 states will use a rate of return regulation, but by 1999, 35 states moved from rate of return regulation to price cap regulation. So the typical rationale for price cap regulation is that it is simple. It requires very minimal administrative cost, and also it will maintain the incentive for the firm to reduce its cost, right? So in this paper, we show that there is also robust rationale behind the price cap regulation. On top of that, our piece rate subsidy up to a target price is very, very similar to these feed-in tariffs used in the environmental to promote environmental friendly technologies. So feed-in tariffs usually takes the form of a fixed price or a constant premium. So we were speaking to this fixed price form of the feed-in tariffs. Now, fixed price feed-in tariffs would remove investors, or you can think about the firm, the exposure to low market prices and transfers the associated risk to the policymaker as a risk of excessive subsidy cost. What we want to add to these feed-in tariffs is that the regulator should not just offer feed-in tariffs, right? So it should offer a feed-in tariffs and a cap on the total subsidy that the firm can get. So this would protect the regulator from incentivize too much overproduction. Now, I have 2 minutes. I'll skip the extensions, and I would actually talk a little bit about why we choose this approach, this worst case regret approach. So this goes back to Anton's question at the beginning. So first of all, we want to advocate for a non-Bayesian approach. The reasons are summarized by this survey by Armstrong and Sappington, right? So when we think about addressing the monopoly regulation using a Bayesian approach, sometimes the relevant information asymmetries can be very difficult to characterize precisely. In many situations, it's not clear how we can formulate a prior belief. On top of that, multi-dimensional screening problems are typically difficult to solve. So effectively, we don't know what the optimal Bayesian policy is in many situations, right? Now, within the robust, within the non-Bayesian approach, we want to advocate for worst case regret for 3 reasons. The first one is that the regret has a very natural interpretation. It's a weighted sum of the firm's efficiency objective and the redistribution objective. The second one is that here I use the more relevant, but actually a better answer is that the worst case regret is more about protecting surplus when the market has a lot of surplus to protect, right? So worst case payoff is more about making sure that I don't do terribly wrong things when there is very little surplus in the market. So if, as a regulator, he is concerned about high surplus market scenarios, he should lean towards worst case regret approach. Now, lastly, there is a political economy motivation for worst case regret. This is offered by Savage originally, and this quote is from the worst case regret bargaining paper from Linha and Redner. Suppose the regulator must justify his policy for a group of people who have very different subjective probability distributions. In this case, the regulator might want to regulate in such a way as to minimize the maximum outrage felt in the room. So in this case, the outrage is equated to the regret. Okay, so the main takeaway of our paper is actually very simple. We kind of using this approach, we use this approach to decompose the regulator's objectives into 3 sub-objectives. He wants more surplus for the consumers. He wants to mitigate the underproduction. He wants to also mitigate the potential overproduction induced by his policy. The price cap addresses the first objective. The piece rate subsidy addresses the second objective, and the cap on the total subsidy addresses the last objective. So that's kind of a nice decomposition of how the policy instruments speak to the policy objectives. So that's the end of the talk, and thank you very much.
Thank you very much for an excellent talk. So I'm gonna stop recording.